Okay, so
Yeah.
welcome to the town hall. I wanted to tell you a little bit about the team. So, this Neurosynth project in general and Neurosynth Compose in general has been a very collaborative project. So here are some of the people that have been involved in some of the, last couple of years of features that we've been working on. The team is even broader if you really look at the whole history of Neurosynth. Um, so I'm gonna just, like I said, overview a little bit of what our goals are and what Neurosynth Compose is about, and then go about tell you a little about upcoming features, and we'll jump into questions and suggestions. So I'm not going to belabor this point because probably everybody here knows to some extent, but it is important to remember, why do we do meta-analysis? Why is it important? And there are three big reasons. First one is there is a deluge of data. As we know, the, the amount of papers published every year is humongous. And so it is more than anyone can keep up with. And so we need tools to help us sort through that publication record, all that valuable data that's coming out, and make sense of it. But also, there's an issue of generalizability and power. So basically, for any individual study, how trustworthy are the results? What kind of conclusions can we make from an individual study? And those are limited by the power of the study. Is there sufficient power to actually detect the effects that we want? And also, every study is going to be limited in its generalizability and its ability to tell us more broadly about the effects that we're studying. So the psychological concepts that we're studying, they could be measured in different ways. The populations can vary in different ways. So there's always going to be an advantage in collating data across diverse studies, even if they're supposedly measuring the same thing. So just to jump into power a little bit, because it really is one of the fundamental limitations of individual fMRI studies. You might have seen this a long time ago from a paper from Russ Poldrack, but basically we estimated what the mean sample size is, the median sample size in literature. And so that's that green line on that plot from this David et al. Paper in 2013. And so as you can see, what they found is that over time, the amount of, the average sample size in fMRI studies is rising. But what we did more recently in 2022 is try to estimate that again, using open data. And we found a pretty consistent pattern of increase. But one thing you'll notice is that despite, increasing substantially over time, we're still only at a median of around 30 subjects per study. And so when you actually try to translate that into power, and that's what this graph on the right does, it actually tries to estimate what is the effect size that we can detect with 80% power using the median sample size.
Mhm.
And right, this is just for the earlier sample size, but we can see is that even when you get up to 20 subjects, which is, the median at the time in 2015, you still need a pretty large effect with a size of, the Cohen's d of zero point 0.8 to detect it with 80% power. So even if you extrapolate this to the median sample size we have today, you still need very large effects in order to be able to reliably detect them using the median sample size. And so, again, this is one reason meta-analysis can be useful because we can overcome some of the limitations of individual studies by combining them. And so that is effectively what we do here, right? We're trying to find studies that measure similar or the same things and build them into what we call a study set. That is a core concept in Neurosynth Compose. And each study is going to be a publishable unit of research that reports coordinates or perhaps images in the future is something we're looking into. And so voila, we can, combine these studies and get very robust estimates of the brain activity associated with certain concepts. So here's an early influential example, a meta-analysis of emotion. And they found patterns that we have seen to be robust and are now fairly well established. But at the time, it wasn't so obvious because any individual study might have only reported a subset of these findings, right? So this is a meta-analysis of 162 studies. Now, meta-analysis is great, and as you can see, it's been around for a while. So what is new? What is, one of the challenges is that we want meta-analysis to be part of the research cycle. So currently, meta-analysis is still a fairly specialized tool that not all laboratories use. So it's something that, a relatively small number of laboratories use on a regular basis. And part of this is because it's simply very time intensive. So meta-analysis is something that takes a long time of manual effort. And our goal with Neurosynth Compose is to make meta-analysis part of the research cycle. So it's something that people can use, even if they're not meta-analysis experts, and they can use this to inform their vision for their lab and their hypotheses. Again, one of the challenges with traditional meta-analysis are primarily that it's extremely time consuming. There's a lot of manual annotation to be done. And because everybody does this differently, ultimately you have inconsistent and localized data storage. So you might store your coordinates in an Excel spreadsheet and put those in your Dropbox, but those never see the light of day. So then when somebody goes and says, hey, I want to ask a different question from this meta-analysis about executive function, I think that executive function is divided into these different domains that they originally tested, I'm not going to be able to reuse your data to answer that question. So I'm going to have to start from scratch. And so that obviously limits the number of questions that are asked from meta-analyses. And ultimately is just it's sort of unfortunate that a lot of this collaborative effort that we put together hasn't been centralized. So that's another goal that we have in Neurosynth Compose. Now, let me take a step back and talk about Neurosynth 1.0. So you might have, be familiar with Neurosynth, neurosynth.org. And this was a really pioneering platform because what Neurosynth said was, well, meta-analysis is really hard. So what about if instead of doing manual meta-analysis, we automate the process by automatically downloading a bunch of studies and then doing, basic NLP type analyses on them. So basically looking at the text of the studies and trying to see if the words in the study are related to different patterns of activities reported in the tables of the study. So basically, Neurosynth extracted the words in the study as well as the coordinates reported in the study and was able to perform automated meta-analyses using the terms. And somewhat shockingly at the time, this actually worked. This very sort of simple and not, somewhat dumb approach of just taking all the words and seeing if they correlate with coordinates actually worked and actually yielded maps that do relate significantly to established concepts. So for example, here is a map of pain, and more detailed pain studies have actually corroborated these maps. However, there are some pretty obvious limitations to this platform. So the main one is that simple text mining can only tell so much about theory. So terms are not really theory, right? So if we want to test more distinct concepts that we might hypothesize about, it may not be possible to do so with this tool, especially in the way it's currently built, which has a static set of terms. And another big limitation is that all of the coordinates in the study are pulled together. Neurosynth did not have an ability to distinguish different contrasts reported in a study. So obviously that makes no sense for a study that has very different contrasts. If I have a study testing PTSD compared to controls and then controls compared to PTSD, I might report both of those contrasts, which are pretty much the opposite contrasts. So if I combine them together into one pool set, that doesn't necessarily make a lot of sense. And that's definitely going to limit the results that you get from Neurosynth. And related to the underlying infrastructure, it was a one-size-fits-all architecture. So basically, it was designed to do one thing, and it did it pretty well, but you couldn't flexibly use the tool. So these are some of the limitations that we've been looking at and trying to overcome with Neurosynth Compose. So the vision for Neurosynth Compose, there's four main goals. The first one is that we want to be able to combine the scale of Neurosynth with the precision of experts with theory-guided hypotheses. So we want to automate the data collection and the extraction, but we want to have experts in the loop and be able to define concepts that they find interesting. This enables targeted hypothesis-driven meta-analyses, right? So not just these data-driven meta-analyses, but these expert-driven meta-analyses. And in terms of the infrastructure, we want to make meta-analysis modular, transparent, and reproducible. So we don't want meta-analysis to be something that is, in your file drawer, in your Dropbox, but something that actually uses, interoperable standards compliance specifications to share your data and contribute to the greater understanding of neuroscience. And this lets you also turn your meta-analysis itself into a shared and reusable asset. So these are sort of the underlying, goals of the project. And they've all come together into Neurosynth Compose, which you might already know about and is already live and is this free and open platform for neuroimaging meta-analysis. I think this is a little bit outdated. I think now we have over 30,000 studies indexed in the platform. So I'm going to now walk over the main steps and concepts in Neurosynth Compose and how they relate specifically to a Prisma-compliant manual meta-analysis. And so the first step is search, right? So when you do a meta-analysis, the first thing you have to do is identify studies that may be relevant for your hypothesis. And traditionally, what you would do is search external sources like PubMed, which already index the biomedical literature. And so what we've done to facilitate this is we've already pre-indexed a lot of a lot of individual fMRI studies in our database that we call Neurostore. And the advantage of that is that those studies are pretty much already likely to be neuroimaging studies. Most 99% of them are. And we've already pre-extracted some features from them. So using the studies in the Neurosort database is going to facilitate the rest of the process. But of course, to also enable any meta-analysis that you might want to do, we allow you to import from your own sources. So you might be able to search PubMed still. You have some reference managers that you want to import studies from. And we also allow import from the BrainMap sleuth format. And so once you search from many of these sources, you come up with a set of studies that are ready for meta-analysis. I just wanted to point out that we are working on improving search using sort of AI-driven semantic search and other types of AI-driven features that will allow you to more precisely select the correct studies, because this is still a step that might pull in too many studies for your liking. Because then it leads to the next step, which is curation. So search is broad by definition. The idea with search is that you want to pull in as many studies that may be relevant, because especially for some of the questions that we're interested in, there's only so many studies that may be relevant. So if you define your search too narrowly, you might miss out on a lot of relevant studies. So given that we have a broad search, we know that many of them won't actually be relevant for our final meta-analysis. So curation is the process where the researcher manually at the time, this is how we have it right now in the Prisma study, manually screens these studies for relevancy. And it breaks down into two main steps. The first one is to deduplicate studies, so you don't want the same study in there twice. And then you want to review the titles and the abstracts for general relevancy. And then finally, you want to do a true eligibility assessment. And this requires assessing the full text of the study using detailed inclusion and exclusion criteria as they apply to your research question. So this is a pretty rigorous and time-consuming step. And Neurosynth Compose tries to make this easier by providing a flexible and easy-to-use interface for applying this Prisma compliant workflow. So this is one of the key features of Neurosynth Compose. It lets you do what you want and what you might typically do in Excel and make it easier for you to do. So once you have, oh, I guess I had some extra things there. I wanted to say one thing about curation, and this is important. This is the scientifically important step, right? So curation is where you are defining your research question, and you're basically saying these are the criteria that define a set of studies that purportedly measure something similar. So I just wanted to highlight this because this is where you have to be critical in applying your scientific question and be specific and transparent in your inclusion and exclusion criteria. What actually defines your research question? What actually is the process you're trying to measure? And what are the tasks or properties of studies that make them eligible? Okay, so now we're done with curation. At this point, we have a set of studies that is a final set of studies. So for example, we might have come from, the original 30,000 studies in Neurostore to 1,000 studies coming back from the search to finally 100 studies that meet all of our inclusion and exclusion criteria. Now, traditionally at the step, what you would have to do is annotate manually all of the coordinates in the study,
Mhm.
right? So you would actually look at the PDFs or the HTML of the study and enter the coordinates manually. Like I said previously, if the study is already indexed in Neurostore, we've already done that work for you. So you will have at least what we could find publicly in the main text of the study available. And your main job will actually be to just verify that information rather than manually enter all that information. Um, and in particular, one thing you might want to verify is that the distinct analyses and contrasts that are reported are grouped correctly. Because one of the biggest challenges that we face is not just pulling the coordinates from the studies, but also dividing them into distinct units. Because like I said, we might have two distinct analyses in a study. We might have PTSD greater than controls and controls greater than PTSD. And we don't want to just dump that into the meta-analysis altogether. We want to perhaps select only a subset of these coordinates. So we have launched a feature recently which uses LLMs to parse these tables into distinct analyses. So this should make your job easier, but part of your job is to verify that this parsing has been done in a way that makes sense for your research question. And of course, at this point, you can also add coordinates for studies that were not in your store. And then finally, really going back to the scientifically important decisions is the annotations. So I want to highlight this because the word annotation confuses some people, but in the context of Neurosynth Compose, what it means is for you to select the analyses and the contrasts that are relevant for your research question. So, for example, again, if I'm doing a meta-analysis on PTSD, I may only want to select the PTSD greater than controls contrast from all the studies and not select the other irrelevant studies for this particular meta-analysis. So this is where you will be selecting the relevant contrast and conditions that are relevant for your research question into the final set that will be added for into the algorithm for meta-analysis. Okay, so at this point, now we have a final study set and we have selected all of the contrasts that we want to include in our meta-analysis. And so now it's, a relatively easy part, which is basically just creating the meta-analysis. So here in the specification stage, you're going to select basically just the algorithm and which annotation you want to apply because you are able to create multiple annotations that define different subsets of contrasts. So you want to select which one you want to run in particular and combine it with an algorithm of choice. We support a wide range of commonly, used meta-analysis algorithms like AL or MKDA. Configure the parameters, that are relevant for your research question and, your thresholding and things of that nature, kernel size. And finally, once you do that, you will be given a unique ID for that analysis. And so this ID will be reproducible because it represents a bundle that is saved in its current state. So even if you go back and make other changes to your project, this is sort of there for future reuse and reproducibility. But it also means that the analysis bundle ID can be used to easily run a meta-analysis. So this is where we get to the statistical modeling. And so we have defined certain well-known workflows for neuroimaging meta-analysis, and you can easily run them in different environments. So basically, everything gets compiled down to a standard format, and that means that they're interoperable with different workflows, some of which we can run your computer. And maybe more of interest to you, most people, is we also have some cloud-based solutions. So you can run the meta-analysis in Google Colab using just that ID. We also have more recently introduced a cloud execution in AWS. So basically, for most meta-analyses that are not huge, we'll actually let you run them for free without ever leaving the platform. And finally, this is all run through Nightmare, which is our Python tooling that implements these algorithms, and it produces an interactive report that is uploaded back to the platform and lets you investigate those results and make your scientific conclusions. Oh, and finally, that report is shareable. So once you decide you want to share that report with other people, you can just make your meta-analysis public and share it with your colleagues, or once you publish the paper, you can actually include that link and share the whole provenance of what you did. So yeah, that's the overall concepts of Neurosynth Compose. Next up, we're going to go to the live demo where James will actually walk through this in more detail. I do want to take a moment to see if there's any questions at this time. And if not,
Hi, I had one question. Sorry.
Hmm.
Um, Nice to meet you. I'm Aaron. I'm based out of Boston. Um, could you talk about more about like the execution engine you have on AWS? Like what tools are you running under the hood, and how do you know what is it elastic? How do you know what to provision so that way it's kind of like a seamless experience or things go as planned?
I'll leave that to James since he's the one that built it.
Yeah, good question. We use Lambda. We use Lambda containers that allow for, I guess, relatively brief amounts of execution or for the decision tree of how long do we execute this for. For slightly longer jobs, we do use EC2 instances that we provision still relatively small, so like two CPUs, 4 GB. And there's certain aspects of our algorithm space that we know is more memory intensive. So we do um, essentially have a flag that takes in the parameter of the algorithm that's going to be run and say, oh, this one requires more memory, so we're going to provision more resources for this one. But that is all done essentially with flags that we control on our end.
Yeah, one thing I'll say about that is that we primarily added the cloud execution for convenience. Um, and in part, we were actually hesitant to do it for a pretty long time, especially me, I will admit that. Because obviously that, cloud gets pretty complicated pretty quick. But at the end of the day, meta-analysis is actually a relatively it's not a very compute intensive job. On the scale of most neuroimaging things, it's actually pretty easy. So we kind of decided, I think it's worth whatever small pains that may be and the cost that we incur because it really adds so much seamlessness to the platform even because a lot of users are going to have difficulty installing Docker, anything that might require local installation is a hurdle that we want to minimize. But having said that, we still have those other workflows because there are certain configurations that you might run into that could potentially overwhelm our deliberately limited resources on AWS. And so we kind of leave that open. So if somebody wants to do something crazy, like some large scale meta-analysis with 30,000 studies, then, maybe better to run that on your own compute. Any other questions right now? And if not, then I'm gonna let James take over, and I'm going to sign off or just kind of hang out in the background. So, but I'll be around in the end if anyone has any more questions for me.
Right. Thank you so much, Alejandro. As he said, I am now going to take over and replace the current share with my own screen. Okay, so if you can see this, this is the Neurosynth Compose main screen. If you've been here before, you've seen this page. And to get started, I'm going to sign in. Doo-doo-doo. And it'll ask me where I want to sign in with. I'm going to sign in with my GitHub profile. And that will show up with all of my projects, which I have many. Okay, so this is the basic uh, page after you log in. If you've created projects, you'll see them along here. If you haven't created any projects, the space will be blank and you'll be encouraged to create a new project. The project is the main area of work. So when you create a new project, it'll give you a whole new interface where we can run through the steps that Alejandro walked through earlier, where we search and curate studies, where we extract and annotate the coordinates from those studies and bundle those coordinates into analyses. And then finally, we can specify meta-analysis with some of our choice of algorithms that were implemented in Nightmare. So to get started, I'm going to rename our project to April demo. And I did say I was going to do an aging meta-analysis, but if anyone wants to write down in the chat right now what meta-analysis they'd be interested in seeing, I can walk through that example instead. Um, so I'm going to select a Prisma workflow, or at least a poor facsimile of whatever perhaps complex question that you're trying to answer. I'm not going to spend all of the time to meticulously go through each of the analyses, but we can see how close that we can get to a meta-analysis. But if no one puts anything in, then I'll search older adults and cognitive control tasks that I'm interested in. Okay, so from here we have the search functionality, which allows us to search our internal database. And over here, we have import studies, which allows us to import studies from different sources that are outside of our own database. So in case you are doing an exhaustive search, either on PubMed or if you've worked with BrainMap before, we have sleuth files, which is their primary format. Or if you've been collecting studies through your own bibliography, such as EndNote or Zenodo, you can import them using this option. Or if the study just does not exist anywhere else, but you want to have a representation of it, you can manually create your own study here. For today's example, I'm going to primarily be searching on our own database. So when I click there, we get over 30,000 studies that have coordinates with them. We do have more studies that are on the database, but not all of them have coordinates associated with them. Some of them have images, and some of them currently do not have images or coordinates associated with them that other users have added and have not completed adding coordinates or images to those studies. Okay, so I'm going to search for, uh, say, aging and Stroop task. Because if I'm interested in cognitive control, Stroop task uh, is one of those tasks that's very indicative of the concept of cognitive control within cognitive neuroscience. So I can put in that search phrase. I can re-verify that the studies that I'm importing make sense to me, and then hit import. And with the first stage, it just does duplicate detection because that's part of the Prisma workflow. We do that for you, and you can verify the results, but you typically do not need to worry about the identification stage as much. We'll promote all studies and screen. All studies that have not been marked as duplication will be promoted, so we'll hit continue there. And from here, we can filter based off of the task name, the group names, the diagnosis. If we're only interested in healthy adults, we can filter this and choose different aspects that say healthy men, healthy older adults. And these are all features that have been extracted via our large language model workflow. And we are actively working on normalizing some of these names so that you can just select, say, healthy or healthy with some conditions and make that easier to filter with. So with that diagnosis filter selected, I can click on this square box, and that will give me the option to promote to the next stage. So I can click that and move them all to the next stage because screening, uh, I'll clear the filter. So screening is mostly about determining whether or not the study is relevant for your meta-analysis. Again, if I wanted to just look at the individual studies themselves, I can click on an individual study and look at the title and the abstract. And I'm really making a judgment at the screening stage based on the title and the abstract to see if it's relevant. And I can use those LLM features as a helper if I want to uh, filter studies based off of information that I would otherwise glean from the title or abstract, which I just did. Okay, so looking at the studies, I can say, let's go back to the table view. And let's say I decided that this import wasn't very good. Like I accidentally typed in a word that I didn't want to type in, and I just want to redo my import. So I can go click on the actual import that I did and delete the entire import. Ask me if I'm sure. I'll say yes, and that clears my space again. So if you accidentally add something to your creation board that you did not mean to, this will make it so that you are not completely bought into that result. You can start over from a fresh slate. So let me, instead of aging, I'm going to look up older adults, because perhaps aging isn't as specific as I want it to be for people over 60. And say Stroop task. Okay, search. So that will give me a much smaller um, number of studies for import. And then I'll import these and all the duplicates. So I'll promote them over here. And I want to filter based off of the age, but all these studies looking at it look relevant to me based off of my very cursory glance. And then in eligibility, I'll add a new column and I want to look at, say, the minimum age. So I want to filter the minimum age to be, say, above 60, because that is what I decided. So 60 to whatever the maximum will be. Okay. And so from there, I can take these studies and use that as my inclusion criteria for being included. I might have more inclusion criteria, but for right now, I'll just use that as an example. So for these other studies, they are either not reported or this one is disqualified. So I can give it a specific exclusion reason, say too young, and that will be excluded down here as a part of my exclusion reasons. Okay, then from here, I can click on an individual study. So there wasn't information extracted from this one. So what I can do instead is open up the paper in a split view, and then I can see if I can find that information myself. So age greater than 60. So I found age, and so that meets with my inclusion criteria. And so I will say include. And then I could do the same for this one. I'll just include it. Okay. And now we went through this entire process, and this button has become acceptable for us to click. So this will move us to the next stage of extraction. But before that, I'm going to add in a few more studies. So I'm going to just put in a couple more searches since we can put in multiple searches here. I'm going to search for older adults, and let's look at the flanker. And I'll import all of these. And then I'll do another task. Let's say older adults and Simon task. Let's see, we'll add in some of those. And then we'll do um, older adults and the AX CPT. I think how you spell it? Just one. And then we'll do one more with older adults and back. Take all those, import. Okay. And then we can do the same process that we did with that first import, and we can see the number of studies that are found with each of the search terms that we used. promote all studies. And then I'll do the uh, easy, cheap thing and just promote all these studies and go to the next stage. Then I can include all of these studies, and that puts them all in the included column. If for some reason, let's say I import some studies via PMID list, and I'll just put in some bogus PMIDs next. And we see the import represented here. See 123, 1234 is not a very informative name, so we can change the name of our imports as well. So we can say this was my bogus study import and save it there. So now you can give your imports meaningful names based off of whether it came from your bibliography, what was the PubMed search that you used specifically, or any other demarcating information that you wanted to include. With this, I am going to delete this import because it does not contain studies that I want. So I'm going to delete that one. And we can move on to the next stage. I'm going to click Start Extraction here. It's going to give me some information about how I can interact with the extraction phase. So this means I can review the information from the studies themselves and start tagging analyses that come from the studies, and analyses meaning contrasts from the papers themselves. We'll get started here. It'll take us through, and now we have our extraction interface. So to get you oriented here, we have our April demo project. We're in the extraction phase. If I click back here, we see we have now finished with the search and curate, and now we're got pushed into this extract and annotate phase. So I'll continue editing here. And the biggest thing here that allows you to move on to the next stage is being able to select this green check mark for each of the studies. And once all of these are selected green, you can move on to the next stage. So I'm going to look in here and click on one of the available studies. Within the study, we have table 3, table 4. That's not super informative. But we do have other versions, perhaps, that could have more information associated with them. Okay. So looking at this other version of the study, so it always helps to, if there are multiple versions, to check them out to see if they are meaningful differences between the different versions. So this one looks a lot more informative, where we can look at sham depletion versus acute tryptophan depletion. So that gives us a lot more information from our either another person's edit or from one of our LLM models. It helped extract this information. And again, if you wanted to verify that everything was correct, you can open up the side window here, and it will take you to the paper, or we can go to, that's the PubMed link, or we can go strictly to the DOI itself, and that will pull up the article. And this will be based on your own subscription to the articles. So this is assuming that you have access to the full text of the article. We cannot provide full text to all the articles because not all of them are open source. Okay. And let's say, based on reading this, I decided I don't want to include the tryptophan depletion group, so I can deselect this analysis and hit the save button here. And that will mean that this particular set of coordinates will not be included in my meta-analysis. And let's also say I want to create like a task type annotation where I annotate whether or not it was a Stroop task or another type of or another type of task. So this one was say go, no go, and I can label it just like so. I can also say go, no go. Now I'll hit save again, and now that one's saved. Okay, then we'll move on to the next study. And we can see that here. It's very detailed information. If I did decide that, oh, the coordinates were not accurate, I took a look inside the paper and decided that the coordinates were not accurate, we can edit the coordinates ourselves. I'm not actually going to edit these coordinates because uh, these ones are accurate. But if I wanted to edit them, I could. And if it was missing coordinates, I could add in a number of rows, and this would allow me to insert more coordinates into the view here. And wonder if it allows me. And I could do things like that, but typically you'll be copying and pasting from an actual table or inputting these rows manually for the ones that are not extracted accurately. And you can also add in a singular row. We just have multiple options in case you need to add rows in bulk, or if you just need to add um, one at a time. 21, 11. Yeah. And from here, we can do the same thing to name the different analyses. So we can give it a task type. This one could be called like an MBAC task. And save that one. And again, that's similar functionality. If they're all MBAC, then we can copy, paste, or just extend that so that it represents NBAC for all of the tasks. So that is what I'm doing here. So we are hoping to make this process just a lot more smooth than everyone's current Excel worksheet workflow or anything else that is not actively being recorded and saved. So I can type in the M back there and hit save, and it is all saved right there. And I'm not going to do this for all the studies. So I think that gives a good overview of the features that we have. I guess within one of these studies, you can also select that when you're done, you hit complete. If you want to look at it later, you can hit this button, uh, and you can filter based off of that status. So if I wanted to have a save for later one that I looked at, but I want to look at later, then I can filter and say, oh, I just want to look at that one, or I just want to look at the completed ones, or I want to look at all the ones that are unreviewed. And so you can filter based off of that if you come to this for multiple sessions. For my example, I am going to mark all these as complete and advance to the next stage. So from here, we can now create a meta-analysis. We've done all the work of searching and excluding our studies and then marking them up with our annotations here in the extraction phase. And we are now ready to create this meta-analysis. So we do offer several different algorithms, and these are all implemented through Nightmare, which is our meta-analysis execution engine. So if you see a missing algorithm or have something that you'd like to run that is not available here, we would love to work with you in Nightmare to get that implemented and then presented on this platform. The default we have is multi-level kernel density analysis. So that is the one that I'll be using today, but we do have other options as well. And here you can specify different arguments that are available within the Nightmare API interface. But for most people's uses, you do not need to edit the algorithm or the corrector for getting just started out. Once you are ready for a publication, Ready meta-analysis, we do recommend you try the family-wise error rate correction, since that one is a little bit more accurate in its correction properties of the statistics. So you can be more confident in the results when you use the FWE corrector. And from here, we had that default column included, but we can select test type as well if we wanted to say, I only want to run a meta-analysis on the NVAC. All the studies I label as NVAC. So that is the way that you can do that. Since I didn't label all the studies, I'm just going to go with included and include everything. And here's a drop down to see all of the studies that were included from this. So yes. If that looks right, then you can move on to the next one. We have a nice little summary here of like 39 studies, 140 analyses, and 866 coordinates. So we'll move on next. We'll say, this is an okay name for me, and I'll create the meta-analysis specification. Then from here, I can run it on AWS, as Alejandro mentioned, or on Google Colab, or even locally. So I'm going to run it on AWS here. And that will kick off a job on AWS, and we will be able to look at the logs from the job as they update. This will take a couple minutes for it to, let's see, yeah, for it to update. So I think sometimes the front end is still, when it doesn't get an update in a little while, the front end is like, oh, something went wrong when nothing actually went wrong. So we'll talk. Uh, we'll hopefully get that updated in the next release so that when it actually runs, you'll be able to see it running without getting that message. And if this does fail for whatever reason, and you want to have a little bit more control in how you run it, you can open up the Colab here, and this will open up a Colab notebook where I copied and pasted this particular ID, and I can type it in here and run this notebook. And really, this just executes the different code bits for you that you don't need to write code to do this. It'll just run it for you because we have it written out. We have it written out here. And we'll see if this one is finishing up. It looks like it is now running through the entire process and has successfully ran. So from here, we get the results of the meta-analysis, and the brain maps are uploaded to another service called Neurovault and then are served on here. So your maps are now shared and accessible for you and your collaborators for running a meta-analysis. And for the corrected map, we also get a table of the results here. So you can download this table of results and do with it what you will, or download the actual Nifty images from the meta-analysis to use as perhaps a prior map for another downstream analysis or whatever that you want to use it for. And you can download this image if you want to put that in a publication. And I think that is about everything that I wanted to show. If you are working in in a space where you want to keep your information private, you can switch your project to private here. But other than that, I think that is everything that I wanted to share about Neurosynth Compose. And yeah, I'm excited to see what everyone would like to do and what they would like to get out of Neurosynth Compose. So from that, I'm going to stop sharing and allow people to um, ask questions. Okay. So I'm going to open the floor for people to ask questions. Thank you for listening to my presentation. Does it all make sense now? And then before you go, I am going to share another. Let me pull that up. I'm going to share a poll for the end of meeting poll to see if after going through that demo, do you feel more confident in running a meta-analysis? And if there's any other, and if you'd like for us to follow up with you for any particular questions or particular project ideas that you have that we could help you with.
There's a question in the chat, James.
Oh, I see. Is there a way to
Is there a way to
share?
share projects to another
Mhm.
person's account without making the project completely public? Currently, there is not.
Yeah,
That
the
is
only
something that
way,
we've been talking about.
yeah,
Um, we know that some people want to be able to collaborate. Um, so that is not something that's currently available. But one thing I will point out, and maybe we can make it more obvious, but at least the results, the maps that get saved to NeuroVault, those can be shared fairly easily. They're basically private link. So if you just don't share that link with anybody, they won't know how to find it. Have you got anything to
yeah.
add to
I
that,
think
James?
there's one hacky way to get around it. If you create an email that is just used by you and your collaborators, then you can essentially have a private a private version that is only visible to you and anyone else that can log in via that created email account. Um, but that would be the only hacky workaround that we currently have for that. It is something that's currently on the roadmap.
Yeah, good feedback. So I think even before we haven't done the fully collaborative mode in part because it's actually somewhat complicated to be honest with you because we need to make sure that people don't delete each other's contributions and so to make it a fully fleshed feature it would be more complex. But I think adding just a private share link that might be something we can look at. So maybe like a view only private share link I think might be useful. And then there's
Yeah.
another question which is if there's any other modalities supported. No, there isn't. And
Mm.
so what I can say right now is the main things that are supported are coordinate-based methods, right? So you also have things like PET and BBM, both of which report coordinates. So although our platform is not exclusively focused on that, um, we are sort of trying to find more of those studies and index them because effectively you can use the same meta-analysis methods on them. However, tractography is actually kind of a different beast. And so I can just give you a preview that we are working on a separate project for that. We're working on a grant right now with Franco Bastilli. Um, and, in his group to basically look at what meta-analysis for tractography would look like. But it's basically completely in its infancy as a whole. But that is something that we have on the horizon.
Yeah. Yeah. I would say exactly what Alejandro said. We are looking to um, differentiate between some of the imaging modalities itself as well, between PET, fMRI, and say VBM studies, so the structural studies. Um, and I didn't, oh, I forgot to go over some of the future directions, but we are working on image-based meta-analysis as well. So that would be looking at a value for each individual voxel as opposed to um, just the sparse handful of coordinates that you get from these studies. And that is an exciting direction that we are looking forward to. If anyone is interested in trying to do an image-based meta-analysis, we do welcome you to reach out to us. So you could get involved with some of our early stage processes of making image-based meta-analyses accessible.
Yeah, just to say a little bit more, image-based meta-analysis, the techniques actually already are implemented in NIMR. So we know the algorithmically, it's something that we can do. The main challenge is that unlike coordinate-based where you can find the coordinates reported in the paper, image-based, you need the actual raw statistical image unthresholded to be shared with you. And so currently, it is theoretically already possible through NeuroVault to do it. We're actually working on developing a front-end, user interface for doing so. So for selecting the inputs from NeuroVault, where people have already shared their images. However, the main limitation is that, only about 5% of the literature or less has images shared for any given paper. So, and realistically speaking, for a lot of these image-based meta-analyses, it's going to require people to reach out to colleagues and have them share maps. So we're sort of trying to look holistically at what that process looks like and integrate it into a user workflow. So, people can actually more easily reach out to colleagues and like keep track of how, which maps were shared with them, upload them. So kind of integrated workflow for collecting and then ultimately meta-analyzing maps. But it's a really exciting direction because IVMA is actually much more powerful in many ways than CVMA. So be on the lookout for that. It should be coming out to some extent in the fall of this year.
Mhm.
Okay, cool. I don't see any other questions.
Yeah, well, thank you so much for giving your time for us and letting us show off some of the features of Neurosynth Compose. If you ever have any questions, you can reach out to us either on the platform itself or reach out to us via email or Neurostars. We have multiple venues of contact information. Thank you all for participating. And
All
thank you,
right, thank
Alejandro.
you.
Thank
Thank
you.
you. Thank you.